So the way SocialVPN deals with this problem is we have the peer-to-peer identifiers, as we saw earlier, and then the node, each node in the SocialVPN issues a self-signed public certificate with that identifier, and that's published through the online social network. And you discover and exchange these certificates through the online social network APIs, for example, XMPP. Now, the IPv4 addresses that are seen by applications are mapped to these P2P identifiers, much like we saw the DHT mapped IP addresses to P2P identifiers in the regular IPOP. Here in SocialVPN, this mapping will be done in a different way. So each user will create a private network address space and will map their users to that private network address space. And the IP addresses will be translated in the process. So here's one example. Let's say Alice has created a local virtual private network in the address space shown here, 192.168.0.0 with a net mask of 16 bits. So that's an address that Alice has for herself, for her SocialVPN, that does not collide with her local address, for example. And she assigns herself an IP address. The SocialVPN software assigns itself an IP address for Alice, in this example 192.168.0.1. And then every node that is a friend of Alice will be mapped dynamically to an address in this range. For example, Bob may get 192.168.2.2. And the mapping between this virtual IP address and the P2P overlay address of Bob is stored by Alice. So that's private to Alice. It doesn't have to be shared with others like it was in the group VPN through the use of a DHT. So when Alice sends a packet to Bob, there's a process of translating addresses here. So the packet goes with source 192.168.0.1, destination 192.168.2.2. But it's translated in the path by the SocialVPN router to the addresses that on the other side here are the source address as seen by Bob for Alice and the destination address, which is the local address of Bob. Now Bob has its own virtual private network with its own local address space. Let's say here another private address space 172.168.0.0 with net mask 16. And Bob, again, SocialVPN assigns itself an address within this address space and maps Bob's friends dynamically to addresses within this address space. So let's say Alice got 172.16.3.4. So again, when a packet comes from Alice, it's translated so it's mapped with the source address to be this one, and the destination address would be Bob's own local address. And when a reply goes from Bob to Alice, it gets to be translated in the other direction. So we do a sort of network address translation to deal with this limitation of IP addresses, but there's no need to translate ports. This process only translates addresses. These are for IP addresses. We have also in the SocialVPN a mechanism to map names, DNS, decentralized DNS for this type of VPN. And the approach here is you don't want to have a single authority that decides on names. You would like to be able to for users to assign their own names that are only valid within the scope of these VPNs. And these names can be mapped with the help of friends. So for example, if you have a machine and you want to call it my machine or Renato's machine, you want to generate your own name for that machine, you try to establish that name and you disseminate it to your friends. And if there are no collisions with other names in the network, your friends will be able to use that name to refer back to you without all of you having to agree on a single authority that determines names in a hierarchical fashion like it's done on the internet today. So in the regular internet, what you have is Alice tries to access a resource, and that name is resolved through a multi-step process. So in theory, you would go to a root DNS server and then go to the levels assigned in this DNS name until you get an IP address, and you resolve it and you can access through the IP layer. We don't want to have centralization and a hierarchical structure, so rather what we have is a mechanism where Alice tries to find a resolution for a name that she has obtained, for example, from Carol. Let's say Carol.sdns is a name that Carol gave for her own resource. So Alice will send a query to her friends and request whether someone has a mapping for Carol in this social DNS namespace, which again is completely decoupled from the physical internet namespace to avoid collisions. So it's not a .com, a .edu, it's a social DNS naming subspace. So Bob may not have that mapping, but Carol may have that mapping, and Alice will get the IP address that it maps to, and Alice in this case doesn't have to remember Carol's IP address, and rather a simpler to remember, simpler to use name. Now if you have multiple mappings for the same address, Alice will be presented with an interface where she can choose which of the mappings she would like to use. So the user interface for the SocialVPN and social DNS would look something like this. You have a web interface where you can log into the service, to the SocialVPN, and automatically you get friends pulled from the social network, and you see that they have virtual IP addresses assigned to them. So let's say an Alice machine, another Alice machine, a third Alice machine, each one with an IP address. And these are the social DNS names that are bound mapped to these addresses in this particular case. But this user interface is only to log in and to look at your users, your friends' IP addresses and names. But from the application perspective, what you have is again a TCP/IP stack available with the caveat of the private user private addresses and the kind of address translation that I explained a few slides ago.